The final thing I'd like to do with our Newton-Raphson method, or I should say methods, is to introduce you to some generalization of this approach. So far we have limited ourselves to just solving one equation at a time, a nonlinear equation, and also only one root at a time. Well, we are going to have to stick with the one root at a time. We don't know how to fix that issue very well other than just moving our starting value somewhere else. But it does turn out that there are generalizations that allow us to solve multiple nonlinear equations at once using a vectorized approach to the Newton-Raphson algorithm. So we'll take a look at that for a little bit. And we'll also make a few other comments about its applicability for complex functions. It's been generalized to work with complex numbers as well. And you might wonder why you even care about complex numbers. Well, it turns out they have quite wide and important applications, particularly on applications that go through some sort of wave or cycles or vibrations. So let's take a look briefly at that. We won't spend too much time at this, but I do want you to have at least a familiarity with the concept. Here we have a system of nonlinear equations. Previously, up to this point, our Newton-Raphson algorithm only dealt with one variable at a time. And we might have a fairly complex function that we were finding the root, but that would be it. We would have one function and one variable. Now we're going to allow an arbitrary number of variables and the same number of equations. So it kind of looks like a linear system, it's just not linear. We will apply, or maybe we will generalize this Newton-Raphson equation to work in a matrix and vector environment. And you're not going to like the looks of it, but here we go. This is what you're going to have to do. Instead of finding the derivative of your single function, you have to find what's called the Jacobian of a matrix of functions by the various variables. So you're going to need to differentiate all of your functions, which are indicated in rows, by every single variable you have using partial derivatives, that being the Jacobian, and we call that J. The other change we need to make is our solution will be a vector. And what we have is the k plus first iteration of the vector solution x, meaning x1 through xn, will be the previous vector plus an adjustment vector. This adjustment vector will be the inverse of the Jacobian times the vector function of the vector solutions. So the vector function is f1 through fn, and x of k is going to be x1 through xn on the kth iteration. That's kind of a mouthful. It seems like a short equation, but I think it's pretty obvious that that's not all that simple. But this is the form that we'll be using, and you'll be putting that in a loop just like you did for the one-dimensional case in order to solve numerically the roots of our vector-valued function. We could create a particularly nasty example and make it a homework assignment for you. Or I could be a little merciful and say, this is a good thing to know. Maybe we'll take a look at that in a graduate level class someday and leave it here for just exposure. And I'm going to do the latter. So that's going to make this whole section way shorter. We've now said everything we're going to say about this vector-valued approach to coming up with a solution to a system of nonlinear equations. We're going to say equally little about the other application, and that is to complex functions. We'll also leave that to a more sophisticated class at the graduate level. But if you do look on pages 134 to 135, your author has done the work there for you in case you're interested or someday you need a reference to it. The solution is there, but we will leave that to another course. So this has no homework in it. How's that? Not too bad. And we will not only end section 3.2D, but we'll end the entire section 3.2 all together. And that will leave us one more section, which we'll call 3.3. And in that section, we're going to ask, what happens if you don't have a functional form. Maybe you have a table or you have to interpolate values to get your secant line, and we will use what's called the secant method instead of the tangent method that we used in the Newton-Raphson algorithm. So we'll do that next time, and that will complete chapter 3 of your text. See you then.